Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we will continue our discussion of Le Chatelier's principle by taking a look at how the addition of a catalyst could potentially affect the position of the equilibrium for any given chemical reaction. Also, we're going to go ahead and revisit the concept of the reaction quotient Q and the equilibrium constant Kc, and we're going to see how those two constants can be applied to Le Chatelier's principle to help us predict how the equilibrium will shift. So we'll take a look at that after we talk about catalysts. And so from our lecture videos on kinetics, we learned that the purpose of a catalyst is to speed up the rate of the chemical reaction. And the way that a catalyst does that on a potential energy diagram is to lower the activation energy. So looking at this potential energy diagram, if we follow the path in green, that's going to represent the path for an uncatalyzed reaction, where the activation energy is much higher than the activation energy for a catalyzed reaction, which is the path in purple. And so when a catalyst lowers the activation energy, it doesn't only lower the activation energy in the forward direction, but it also lowers the activation energy in the reverse direction. And so if we look at this potential energy diagram, and if we follow that path in purple from reactants to products, we can go ahead and follow the same path in the reverse direction. And so since the same path is followed, then the catalyst also lowers the activation energy in the reverse direction. And so because the catalyst lowers the activation energy in both the forward and the reverse direction, it affects the rate constants in the forward direction and the rate constant in the reverse direction equally. And so since it affects both of these rate constants equally, the ratio of the two rate constant, K forward and K reverse, will remain constant, and therefore the equilibrium will not shift in favor of the reactants or the products if a catalyst was added or is present in a chemical reaction. And so once again, if a catalyst was present in a chemical reaction, overall there would be no shift in equilibrium. It doesn't favor the forward direction or the reverse direction because the catalyst acts equally on both the forward and the reverse reaction. So that's pretty much it for catalysts. So overall, we talked about 5 stresses that can be applied on a chemical reaction. We talked about how concentration, changes in concentration, changes in volume and pressure, changes in temperature, not so much change, but the addition of a catalyst or addition of an inert noble gas affects the position of the equilibrium in a chemical reaction. And so let's go ahead and discuss how these factors, how these stresses affect the actual value of the equilibrium constant Kc. And so it turns out that changes in volume, pressure, and concentration does not change the overall value of the equilibrium constant. What it does is that it changes the position of the equilibrium, which is going to be represented by Q. And we're going to go ahead and illustrate this concept a little bit later down the line. For now, just take it for face value that the changes in volume, pressure, and concentration does not affect the overall value of the equilibrium constant. It just affects the current position of the equilibrium, which is represented by capital Q, or the reaction quotient. For catalysts and inert gases, the addition or presence of them do not affect the position of Q, and it does not affect the overall value of Kc. So we have kind of two extremes here between volume, pressure, concentration, catalyst, and inert noble gases. Right in the middle, we have changes in temperature. And so if you were to change the temperature of the surrounding of the system, not only does it affect the position of the equilibrium Q, but it also changes the overall value of Kc, of the equilibrium constant Kc. And what we want to ask ourselves is why. And this is something that I've already addressed in a previous lecture video, but let's go ahead and revisit this concept. And so if you recall, the equilibrium constant Kc is simply a ratio of the two rate constants, K forward and K reverse. And the concentration of the products raised to its coefficient divided by the concentration of the reactants raised to its own coefficient simply represents the mass action expression for the equilibrium constant Kc. And so if we were to change the concentration of the actual reactants and products, whether we're changing it directly or indirectly through volume and pressure, what we're doing is we're changing the actual concentration so that the equilibrium concentrations of the product and the reactant is going to change, but the actual value of the equilibrium constant Kc does not change. And so we can go ahead and understand this concept by looking at the rate law. And so if we're changing the concentration of the reactants and products from one equilibrium to another equilibrium, we're only changing the rate of the forward and changing the rate of the reverse reaction. However, changing the concentrations of the reactants and products, whether it's directly or indirectly, does not affect the rate constant of the forward and the rate constant of the reverse. And so, because these two constants are not affected, the actual value for Kc is unaffected through change in concentration, whether it's done directly or indirectly through changes in volume or pressure. Now, according to the Arrhenius equation, the rate constant is affected by changes in temperature. And so looking at this Arrhenius equation, the pre-exponential factor A, the activation energy, as well as R, all three of these are constants. And this little e is an exponential, which is a function. And so the only variable that does have an effect on the rate constant itself is temperature. And so changes in temperature will change little k, which changes these little k's, which changes or alters the actual value of the equilibrium constant Kc. And so that's what these 2 points is trying to get at. And so in this lecture slide, it simply summarizes Le Chatelier's principle with respect to concentration, pressure, temperature, catalyst. It's not a complete summary, but it's a summary that kind of gets you thinking. And so looking at this column, this change, this can be synonymous to the stress that's applied onto the chemical system. And so if the stress was a change in concentration, how would the equilibrium shift? Would shift to the opposite side of that stress, or would it shift to the same side of that stress? And does it change the actual value of Kc? So for concentration, the answer is no. For pressure volume, the answer is no. So once again, pressure volume indirectly changes the concentration of the reactants and products at equilibrium. And once again, our proof tells us, our proof tells us that changes in concentration of reactants and products will not change the equilibrium constant, Kc. So the only thing that does is temperature. Okay. And so what I want to do next is continue covering the concept between the reaction quotient K and the equilibrium constant K. The reaction quotient Q and the equilibrium constant K. And so we're going to go ahead and apply Q and K with respect to Le Chatelier's principle. And so I want to go ahead and draw your attention to this graph. And we've seen this graph once before. And so if you recall, the reaction quotient Q can represent the activities of the products and reactants at any time period. And so since we're talking about Le Chatelier's principle, we know that there are two equilibriums. There's the old equilibrium, where this would be the equilibrium before the stress was applied. And then there's going to be a new equilibrium, which is after the stress was applied. And so Q, for this specific concept, Le Chatelier's principle, Q is going to represent the old equilibrium. Okay. And so this is the equilibrium before the stress was applied. And so all of this is going to represent Q. And we're going to see how changes in Q will lead into K. And so K, the equilibrium constant K, for Le Chatelier's principle, is going to represent the new equilibrium constant. So it's going to represent the new equilibrium, which is the time period in which it's going to happen after the stress was applied. Okay. It's pretty much the end result. And so it turns out that the relationship between Q and K with respect to the equilibrium, with respect to Le Chatelier's principle, is still similar to the concept that we discussed in a previous lecture video, where if the position of Q is less than the position of K, the reaction is going to move towards the side of the products so that the new equilibrium can be reached. And so if the roles were reversed such that the reaction quotient Q, the position of the old equilibrium is higher, if you will, than the equilibrium constant Kc, which is going to represent this new equilibrium, then that's telling us that for the old equilibrium to get to the new equilibrium, products must be converted into reactants. All right, so overall, we're going to explore how changes in concentration will affect the value of Q. And what we're also going to explore how the equilibrium will shift to achieve K, which represents the new equilibrium. So let's go ahead and just explore this topic just a little bit more. So we're going to explore how changes in concentration affects the value of Q, and we're going to see how the equilibrium will shift to achieve the new equilibrium, which represents capital K. And so this concept might seem intimidating, but it's pretty simple. I'm going to simplify the explanation as best as I can. We're not going to go into great details on how it's derived. Feel free to ask me during office hours. And so let's go ahead and take a look at this general chemical equation. And we're going to go ahead and apply some stress. And in this scenario, we're going to add reactant. And so if we're going to add reactant, I'll do this perhaps in brown. So we're going to increase the concentration of the reactant. So that's going to be the stress. And so based on your knowledge of Le Chatelier's principle, how will the equilibrium shift? And so from what we've learned, the equilibrium is going to shift to the right to consume the reactant that was added into the chemical system. And so therefore, at equilibrium, we're going to have more product than we have reactants. And so how does this translate with respect to Q and K? So once again, I'm going to keep this as simple as possible. Remember that the equilibrium is shifting to the right. Okay. And so, actually, I think I kind of misplaced that. I'm going to put it right here. So we know that to achieve the new equilibrium, it's going to shift to the right. And so if you wanted to compare the value of K and Q, or Q and K, what inequality will allow us to best represent the relationship between K and Q when the equilibrium is going to shift to the right? And so if you guys recall from that specific lecture video, we can go ahead and treat the inequality as the mouth of the Pac-Man. And the mouth of the Pac-Man is going to tell us how the equilibrium will shift. And so since the equilibrium is shifting to the right, then the inequality points towards the right, where the equilibrium constant, Kc, is always written on the left, and Q, the reaction quotient, is going to be written, the Kc is going to be written on the right, and the reaction quotient Q is going to be written on the left. And so overall, this is telling us, that the effect on Q would be a decrease in value of Q. So Q is lower than K. And so the value of Q is decreased. Okay. And so let's go ahead and look at our next example. So here we're adding a product. And so if we're adding a product, that means we are going to increase the concentration of the product. And it doesn't matter which product we're increasing, and so I'm just going to bracket both of them. And so based on your knowledge of Le Chatelier's principle, we know that if we increase product, the chemical system will respond by consuming the product, thus producing more reactants. So the equilibrium will shift to the left. And so I'm going to go ahead and just, I'm going to go ahead and just duplicate this. And point the arrow the other way. And so if I know that my equilibrium is going to shift to the left, then what would be my relationship between K and Q? I'm sorry, Q and K. And so since the mouth of the Pac-Man points in the direction of how it's going to move, of how the arrow is going to shift, since the arrow is going to shift to the left, that means that the inequality is going to point to the left as well, such that the value of Q is going to be greater than Kc, than the equilibrium constant Kc. And so Q is greater than Kc. And so what we're doing in a way is that we're kind of working backwards. So now that we know the shift in equilibrium, what's the relationship between Q and K? Okay, and so if it's shifting to the right, then that means K is greater than Q. So we have a decreased value of Q. If the equilibrium is shifting to the left, Q is going to be greater than K. All right, and so let's go ahead and look at the next two examples, and I'll just go ahead and speed up just a little bit. And so we're going to remove a reactant. It doesn't really matter what reactant we're going to remove. So all I'm going to do is bracket both of them, and I'm going to lower the concentration. And so if I lower the concentration of the reactants, Le Chatelier's principle tells me that to replenish the reactants that was lost, the equilibrium is going to shift towards the left. And so if the equilibrium is shifting to the left, I'll go ahead and duplicate this, then that means that the value of Q when compared to K is going to be greater. Okay, so we still have this same scenario. And finally, when I am removing product, okay, it doesn't matter which product I remove, so I'm just going to bracket both of them. I'm going to lower their concentration. And so if I take away some product, the equilibrium is going to shift to the right to compensate for the product that was lost. And so overall, since we have a shift to the right, the inequality is going to point to the right. The mouth of the Pac-Man, or the mouth of the inequality, is going to face the equilibrium constant Kc. And so therefore, we can conclude that the value of Q is going to be less than Kc. Okay, and so once again, what we're doing is we're kind of working backwards with respect to the relationship of Q and Kc. All right, so let's go ahead and apply this concept to a chemical reaction. So let's go from theory to an actual problem. So let's say that this is our chemical equilibrium. We have iron reacting with thiocyanate to produce iron thiocyanate. And so if we add iron 3 nitrate to this chemical system, how would it affect Q, and what would we need to do to the equilibrium so that it achieves the new equilibrium, which is represented by K? And so to answer this, we need to go ahead and keep in mind the solubility rules for all of these substances. So iron 3 nitrate, the chemical formula is Fe parentheses NO3 3. Okay, so there's 3 nitrates for every 1 iron because the charge of nitrate is -1. Now, if you recall, all nitrates are soluble, and so therefore it's aqueous. I'm just going to actually move this just a little bit to the left because I need that space at the bottom. And so because, maybe I'll just move this downwards. So because iron 3 nitrate is aqueous, it's soluble, that means that FeNO3 will decompose to just iron 3 plus with 3 nitrate ions. And so what we're really doing is when we add iron 3 nitrate to this chemical reaction, what we're doing is we're increasing the concentration of the nitrate. So here we're increasing the concentration of the nitrate. Or I'm sorry, not the nitrate, the iron. I don't know why I said nitrate. I apologize. And so when we increase the concentration of the iron, that's going to disrupt the current equilibrium. And according to Le Chatelier's principle, an increase in reactant is going to shift the equilibrium to the right. And so, therefore, to achieve the new equilibrium, the reaction, the equilibrium, must shift to the right. And so, how does this affect Q? This means that there's going to be a decrease in value of Q. With respect to Kc. Okay? And so Q is less than Kc. Okay? So let's go ahead and look at the next example. So here we're going to add sodium thiocyanate. And so sodium thiocyanate is Na SCN. And so if you recall, any group 1A elements that's attached to an anion, in terms of its solubility, it's going to be soluble. So therefore it's aqueous. And what that means is that if you take sodium thiocyanate and you drop it in solution, then sodium is going to separate out from thiocyanate. And so for this example, the presence of thiocyanate in this equilibrium is once again going to increase the concentration of thiocyanate. Thus, the equilibrium is going to shift to the right. And so since it shifts to the right, the conclusion is still going to be the same. Uh-oh. Oops. So if we shift the equilibrium to the right, then we know that the equilibrium constant Kc is going to be greater than Q. So therefore, the addition of reactant is going to decrease the value of Q. Let me be more grammatically correct. Decrease the value of Q with respect to Kc. So last but not least, let's talk about sodium carbonate. And so sodium carbonate, it's Na2CO3. And based on what we just discussed with sodium thiocyanate, the presence of sodium in this compound is going to make the ionic compound soluble. Therefore, that compound is aqueous. And so what that means is that if we take sodium carbonate and we place it inside a solution, the sodium is going to separate from the carbonate. Okay. And so it turns out that this carbonate is going to react with one of these species. And so this carbonate will react with iron, producing a precipitate. And so here, I'm just going to go ahead and just write it in. Okay. And so this carbonate is going to react with this iron, producing iron 3 carbonate. And it's going to be solid. In other words, it's going to precipitate. And so when a precipitation reaction occurs, this free iron, the concentration of that free iron is going to decrease. And so when it decreases, then that alters the equilibrium. And so to counteract the change that was made, the equilibrium is going to shift to the left to compensate for the loss of the iron. And so since the equilibrium is shifting to the left, we know that the inequality points this way, and Q is going to be bigger than Kc. And so the addition of sodium carbonate, it's going to increase the value of Q with respect to Kc. Okay. And so this is how we can apply the concept of Le Chatelier's principle with respect to Q and Kc. All right, and so what else can we do with this? Instead of giving you guys this type of problem, we can also quantify the values to determine how the equilibrium will shift. And we're going to go ahead and address that by looking at this problem. And so first we're going to consider the reaction below. And if the concentration of the phosphate is 0.20 molar, the concentration of hydroxide is 0.40 molar, and the concentration of phosphoric acid is 0.10 molar, is the reaction at equilibrium? And so it told us that the equilibrium constant Kc is 50.5. And so if not, how will the reaction proceed to achieve equilibrium? And so let's go ahead and think about this concept, this problem just a little bit more. So notice that the concentrations of phosphate, hydroxide, and phosphoric acid is given to us. Did this problem indicate that these concentrations are equilibrium concentrations? And the answer is no. And so, since they are not equilibrium concentrations, then these concentrations can be used to calculate Q. And so let's go ahead and calculate Q first. And we know that we can do that by writing the mass action expression. And so looking at the physical states of matter, we have aqueous, and aqueous. And so the reason I ignored water is because it's liquid in state. And if you recall, any substances that are in liquid or solid in state will not be written in the mass action expression because their volume is the ratio between the amount of volume will always be the same regardless of how you change that specific substance. So for example, you can triple it, you can double it, you can halve it. The ratio between the amount and the volume is still the same. So it's not going to affect the value for the equilibrium. So there's no need to include it in our mass action expression. And so what we have here is just the concentration of phosphate raised to the first power because we have a coefficient of 1. And so that's the only product that we have left. And what we're going to do next is we're going to write the concentration of the reactant, in this case is phosphoric acid raised to the first power, times this by the concentration of hydroxide raised to the third power because we have a coefficient of 3. And so since all of these concentrations are not at equilibrium, then we can go ahead and use these concentrations to calculate Q. And so Q then becomes a ratio of reactants to products. So here in this case, phosphate is 0.20 molar. So I'm going to put 0.20 molar here. And then it's going to be raised to the first power. And then hydroxide is going to be 0.40 molar raised to the third power. And then phosphoric acid is going to be 0.10 molar raised to the first power. And so from here on out, all we have to do is plug this into our calculator so that we can calculate the value for Q. So let's see here. Here's my calculator. So if I plug in 0.20, divide this by the product of 0.10 times that by 0.40 raised to the third power, that's going to give me 31.25. And so it turns out that the value for Q is 31.25. Now, based on the problem, it told us the value of Kc is 50.5. And so based on these values, based on these numbers, is this reaction at an equilibrium? Okay, and the answer is no. Okay, so because Q does not equal to K, the reaction is not at equilibrium. And so to address this second question, how will the reaction proceed to achieve equilibrium? Well, all we have to do is just compare these numbers. And so 31.25 is less than 50.5. So notice how Q is written first. So make sure Q is always on the left-hand side, K is always on the right-hand side. And so if we take this inequality as the mouth of our invisible Pac-Man, we know that the Pac-Man is going to move in the direction of where the mouth is pointing. And so therefore, the equilibrium must shift to the right. For the equilibrium to be achieved. Okay. So this is another way that we can apply the concept, the relationship between Q and K, in addition to doing this like whole reverse thing for Le Chatelier's principle. All right, so let's go ahead and look at a summary slide for the effect of K or Q. And so when we're adding the reactant, we know that we're shifting towards products, and therefore Q is going to decrease. Adding a reactant, we're going to shift towards, adding a product, we're going to shift towards the reactant. So therefore Q is going to increase. Removing a reactant, shifts towards the reactant, Q is larger. Removing a product, shifts towards the product, Q is going to decrease. And so all of this is pretty much the same as what we did here. Okay, so here we have Q is lower, Q is greater, Q is greater, Q is lower. And so we're for the other conditions, pressure, inert gases, temperature, we're not going to go ahead, we're not going to focus on effects of Q. It gets a little bit too complicated, but that's okay. So we're only going to be focused on concentrations of reactants, changes in concentrations of the reactants. How will Q change? So that's pretty much it for this lecture video. If you guys have any questions, feel free to email me or Zoom me for office hours. See you later. Bye.